hopefully you guys had an opportunity over the course of the last couple of days to take a look at the 2.4, 2.5 content. Last night I posted a maybe not super quick, but kind of a condensed version of 2.5, which ties in a lot of the kind of stuff that we had missed from 2.4. What I wanted to do today is to get a little bit of practice under our belts with the actual content for 2.4 and 2.5. So a lot of today is going to be a work day, maybe not that much, but a fair chunk of today is going to be a work day. But before we kind of start, before I turn you guys loose to work on either this packet or the classworks that we all have, I wanted to take some time to work through this first example together, just so we can all kind of see how everything is done once, kind of all at once, holistically with 2.4, 2.5. We do have a quiz over 2.4, 2.5 on Friday. And really that quiz could look pretty much like just a single one of these questions. Like that would be a fairly robust quiz that you could expect to do, where you're being asked to construct essentially all of these different representations for our frequency distributions. So I'm going to spend a little bit of time on that, and then you'll have the rest of this time to work on your classworks or on this worksheet. All right, so looking at this first problem here, we are given a frequency distribution, and we are being asked to ultimately graph the various kinds of graphs that we saw in 2.5. But before we do that, we're going to take a look at filling in some of the rest of this information about our particular distribution. Starting off, very first thing that will be prudent to calculate is going to be the total. They're describing it as like the total frequency, but we can just think of this as like the total number of data points. What will I need to do in order to figure out essentially my sample size, how much data I am working with? Yeah, how would I calculate the total frequency?
You just add them all.
Yeah, just add everything that we see together, plug it into your calculator, and what you should get, and feel free to double check me on this, but this should be 255 data points. So just 7 plus 33 plus 68 plus 75, so on. We have a total of 255 kind of instances in which we are collecting data. What was the relative frequency? What's different between like the frequency versus the relative frequency here?
It's like the percentage of. Well, I don't know how. I just know how to get it.
Okay, so it's something to do with like percentages. Essentially, that is going to be like how the percentage that our bucket represents for our overall. I'm going to use that word a lot, bucket, which is essentially just going to be my casual way to describe the class limit. But we're going to say how much, what percentage of our overall data lives in a particular bucket. So how do we calculate it, Merrick?
I don't know. You divide it and times it by 100.
Yeah, so we need to figure out what proportion, what fraction our bucket represents. We have a total of 255, so we're going to be dividing everything by that 255. In this case, we see 7 data points out of our 255, and then absolutely correct, multiplying this by 100, our way to convert a fraction to a percentage. And when we do that, I get that we have about 2.9% for this first bucket. So doing that 7 out of 225, and then multiplying by 100 to get, or no, 2.7 rather. Yep, thank you for checking me on that. 2.7% for that. Yeah. You can round it to tens. I'd probably round it to hundredths if I was being super, super persnickety. But tenths is also perfectly. Just be consistent with the rounding, basically, especially in a case here where I'm not telling you what to round to. All right. And of course, we could do that with each of our buckets. So 33 out of 255 is going to be a little bit more than 10%. In fact, we see that this is 12.9%. And going down the list, finding what percentage, again, these buckets represent. So we're taking we have a total of 255 data points, which is just adding everything up. 7 of those 255 data points live in our first bucket, which is about 2.7% of the data. 7 out of 255. Yeah. And likewise with each of the buckets, that's how we would calculate not 90%, but 9.0%. And then lastly, 4.3%. All right, class boundary was kind of the last thing that we covered on Friday. Very, very similar to class limit. Class limit was like the label that we tack on to the buckets. What's really the only difference between the class limit and the class boundary? What does the class boundary kind of start to account for? It's a little bit more fine-grained than that.
Like you add one more, or like you have to count the...
Only difference between the class limit, which is basically telling us which bucket is which, and the class boundary is it's essentially our rounding rules. All right, so we're going to say if I saw like a particular decimal place, this is the bucket that I would put it in. So if our class limit is 0 to 10, what is kind of the cutoff for the smallest possible value, mathematically, ignoring the fact that we can only see positive values for this particular example, but what would be the kind of cutoff for values that we would put in this particular bucket rather than, say, a bucket that's further to the left than this? Yeah, exactly. That would be, this would be negative 0.5. Anything greater than that is definitely, or anything kind of a little bit greater than that is going to be definitely in our first bucket. Anything less than that, so thinking like negative 0.6, negative 0.7, would not fall within this particular category, right? Would not fall within this particular bucket. And then what would our upper bound be for this particular class limit? Yeah, 10.5. Now notice that technically speaking, negative 0.5 and 10.5 would both round up. In this case, though, we're kind of using them to just say this is like the in-between. It's like the liminal space between bucket A and bucket B and bucket C. If we actually measured something to be 10.5, we'd be in a little bit of trouble figuring out which bucket it actually went to. They kind of share that 0.5 space. So like 10.6 would definitely go to the next bucket. 10.4 would definitely go to this first bucket, but 10.5 is kind of shared between the two, and we're just going to cross our fingers and hope that we don't run into it. Yes. Yeah, so essentially we're just going, it's essentially 0.5 below our lowest class limit and 0.5 above our upper class limit. Now, if that is only because what we're dealing with is in terms of ones. If we were instead in terms of like hundredths, you might go 0.005 below and 0.005 above the respective. So you're essentially just using the rounding rules to figure out what they're going to be. So we're thinking we want things that round into our bucket either rounding up or rounding down, depending. So for instance, looking from 11 to 21, what is the lower bound for things that would fit into our second bucket? 10.5. And what would the upper bound be for things that we would fit in our second bucket? 21.5.
Less than the actual.
Kind of. Yeah. Again, that is because what we see for our class, what we have here, because this is in terms of ones, we're seeing that 0.5. If this was in terms of tenths, then we'd be looking at the hundredths for the rounding. If it was in terms of hundredths, we'd be looking at the thousandths. So we're essentially going 1 degree, 1 magnitude lower, and it's the 0.5 from there. Yeah. Madison, does this make it a little bit more clear how we're getting this? Yeah, yeah. So looking at so we're pulling from these values here, and we're just adjusting them a little bit below, a little bit up to account for the possibility of rounding. All right. So 21.5 would then be our lower bound for the third bucket, up to 32.5, and just going through to 43.5, 43.5 to 54, 54.5 to 65, 65.5 to 76.5. So just like a half tick below the lowest class limit and a half tick above the upper class limit. While we're here, let's also talk about the class width. What is our class width from 0 to 10? 11. You could think of the class width as really kind of taking into account the fact that we're starting at negative 0.5 and working our way up to 10.5. We're thinking about the amount of distance that we have to travel to get from A to B. Then absolutely we have kind of 11 steps to go. But also you could think of this in terms of our kind of counting. If we start at 0, 0, 1, 2, counting all the way up, we see that there are 11 numbers 0 to 10 if we count the boundaries. All right. So our class width here is 11. Now we didn't talk about the midpoint. The good news for us is that the midpoint is exactly what we have been calculating for forever. We're also not really going to do any math with the midpoint. What we're going to use the midpoint for is it's going to essentially be the representative for a particular bucket. So if I want to talk about the contents of bucket 1, rather than talking about every single number that fits between 0 and 10, I use 5 as like the poster child of bucket 1. Or use whatever, a little bit of spoilers there, use whatever the midpoint is for that bucket to be its poster child. All right, so we can kind of do this a little bit intuitively. What's the number that fits perfectly in the middle of 0 and 10? That's going to be 5. If we wanted to actually compute this, 0 plus 10 divided by 2 is 5. You take the average of your upper bound and your lower bound to find the midpoint. And you could do this either with the class limit or the class boundary, and you should get the same answer. It shouldn't matter. Think the class boundary is essentially we're just taking a little step to the left, a little step to the right. We haven't actually changed where the center is, so we should be able to do this with both. So we'll go ahead and knock this out for the others. 11 plus 21 is 32 divided by 2 is 16. 22 plus 32, 54 divided by 2 is 27. 38, 49, 60, 71. These are our poster children for their respective buckets. All right. The final piece here that is a little bit odd, just in terms of kind of being a little bit different as far as what we're actually computing, is what is known as the cumulative frequency. This is mostly going to be used to refer to kind of large sums of buckets. So rather than talking about the contents of a particular bucket, maybe I want to talk about the contents of any bucket that's to the left of bucket 3, or any bucket that's to the right of bucket 5. This will kind of follow from what we do with our cumulative frequencies. We're going to start to the left of our leftmost point, and we're just going to kind of work our way through the buckets. Essentially, as we work our way through, we're just going to slowly sum the contents of each bucket. So for instance, starting out, if I am to the left of our leftmost bound, how many data points do I have? If I am to the left of our leftmost bound, so I'm to the left of negative 0.5. Do I have data? No, I don't have any data. My frequency would be 0. Okay. So now we're going to look at what's going on to the left of our next bound. In this case, this is the 10.5. To go from negative 0.5 to 10.5, I have passed completely through the first bucket. So by the time I have gone all the way through the first bucket, how much data have I covered? I have covered 7. We are then going to look to the left of our next bound, 21.5. How much, all right, really how many buckets have I gone through by the time I go from start to 21.5? So I've gone through how many buckets? 2 buckets for a total of 40 data points, which is coming from
Oh, so you're just adding
7 plus 33, exactly. Yeah, absolutely.
You're just adding, so like. No, don't write it. I did it.
Sure. So thinking of first one is like we've gone through 0 buckets, so we have nothing. Second one is we've gone through 1 bucket, so we have 7. Third one is we've gone through the first and second buckets, so we have 7 plus 33, we have 40 data points. By the third bucket, once we're through the third bucket, how much data do we have? 108, which is that 40 plus that 68. By the time we're through the fourth bucket, we have 183, fifth, 221, sixth, 244, and then finally, by the time we're at the end of our fifth bucket, we're at 255. Does that make sense? Does it make sense that we would end at 255? Yeah, we'd expect that by the time we're at the end of our data, that we would have gone through all of our data. We said we had 255 data points. All of them are accounted for. Nice and kind of corroborating information. So questions here with, so we did relative frequency, class boundary. Hopefully that was good review from Friday, but questions here with some of the new stuff with the midpoint and then the cumulative frequency.
Isn't it supposed to be 60?
I think it should be 65.5 because we're thinking 65, a half tick above 65 would be the 65.5. And a half tick below 66 would be 65.5. How are we feeling here? Pretty good? Not too horrible? Okay, so class limit, the 0 through 10, the 11 through 21, blah, blah, blah. Think of that as like the name of the bucket. We're not really going to use that for our actual like displaying of information. So we generally don't use the class limit. We are instead going to use the class boundaries for a lot of it. And in one instance, we'll see we'll use the midpoints as well. But again, that midpoint is acting as a representative of the particular bucket that we are in. So let's take a look at how we are going to actually present the data that we have collected here. So we're going to start with a histogram. For the first two, our y-axis is just going to be the frequency. If we're looking at the frequency here, we'll notice that 75 is the largest value we're ever going to have to worry about. And so counting up by tens here, I think makes a lot of sense. It's like 10, 20, 30, 40, 50, 60, 70, 80. And by that point, I should be all good with everything that I have collected. If my relative frequency went higher, then of course I would maybe adjust this, but we should be happy as is here. If you need a separate sheet of paper to make it bigger, then I have separate paper in the back. So this is for you. This is your practice for you. I'm not going to collect this. However, you want to draw it in a way that you can make it legible and nice and be able to understand what's going on. Okay. Our x-axis is going to consist of our class boundary. So again, we're not really going to use the class limits, but how we divvy this up is going to be representative of a particular class limit. So for instance, our first box starting at that negative 0.5, working its way up to the 10.5, and then 21.5, 2, 3, 4, 5, 6. We'll go a little bit further here. So negative 0.5 to start. Then we've got our 10.5, 21.5, 32, 54, 65, and 76. Histogram is pretty simple. All we are going to do is we are going to graph every value in between the bucket with the y value that we have for the frequency. So for instance, our first bucket goes from the boundary of negative 0.5 up to 10.5. We saw what frequency for that particular bucket? 7. And so the height of our graph for that particular part of our graph is just going to be 7. Likewise, for our second bucket, which is between 10.5 and 21.5, we saw a frequency or a Y value of 33, like so. We then saw a Y value or a frequency of what, 68? Like so. And then 75-ish. And then 38. 40. And then 23. Ugly. 23.
So it's actually 21.5, 32.5, right?
32.5 was the upper and lower boundary of our fourth and third bucket, respectively. Yeah, so 32.5, notice, fits perfectly in between the third bucket and the fourth bucket as an X value. 43. Plus 11 each time. Notice that from one boundary to the next, we are adding the width. That class width that's getting added from one to the next, to the next, to the next. So plus 11, plus 11, plus 11, plus 11 each time. Which is not a coincidence. That's what the class width is. Okay, part of what we are doing here as well is taking a look at this and determining what shape this distribution has. For now, we have 4 different options in terms of shape. The kind of caveat, the asterisk that we're going to have here is that we are working with data, we are working with the real world. These shapes might not be super exact. As we move forward, we are going to have better ways to understand, is what we are seeing actually reflective of, like, is this a good enough representation for our shape or something else going on, blah, blah, blah. But the 4 shapes are either going to be a uniform distribution, a symmetric distribution, a right skewed or positively skewed distribution, and a left skewed or negatively skewed distribution. Uniform, pretty straightforward. Every bucket is similarly filled. So maybe not, it might not be the exact same all the way across the board. We'd want it to be the exact same. That would be a truly uniform distribution. It would be like if every single bucket had 5 in it, that would be perfectly uniform. But maybe one bucket has 6 and another bucket has 5 and one bucket has 4 and another bucket has 6 and 1. But the point being, all of them are fairly similar. So uniform, all buckets are fairly similar. Does that feel like this particular distribution fits that bill, or are all of our buckets similarly filled? Well, so thinking about the Y values, the frequency. Yeah. So a bucket being filled is like how full the Y value there. No, right? We notice that we have a couple that are barely filled, right? Frequencies of 7, frequencies of 11, and then some that are fairly full, frequencies of, say, something like 75 or 68, things like that. So this is not uniform. The other, one of the other options, symmetric. We have a clearly defined center, so our middle bucket is going to kind of act as a center, and we're going to have pretty similar amounts of data to the left and to the right of that center. Right? So for this particular example, is our middle bucket kind of acting like a center, and do we have similar amounts of data to the left and to the right of that center? Yeah, I'd say so. I'd say that that's pretty close. Maybe there's a little bit more on the left-hand side of our center than the right-hand side, but it looks pretty close, right? It's about kind of centered around this middle bucket, and so we would maybe describe the shape of that distribution as symmetrical. You will also, a little bit of an asterisk here, this kind of shape that we see here will also sometimes be referred to as a normal distribution. Those are effectively equivalent terms. I would say the only real difference between a normal distribution and a symmetrical distribution is the normal distribution is always going to be like heavily weighted towards the center, and you could theoretically have a symmetrical distribution that looks like this, where it's really weighted to the sides and not very weighted in the center. Like this would still be symmetrical. It's just not normal. It's doing something else. It would be called bimodal. Right. But normal is generally what we are going to see with our symmetrical, just certainly not exclusive. The other two are, I find, a little bit confusing just in terms of how they look. So if we have our normal or our symmetric, where we've got like pretty similar distributions with a whole lot in the center, we've got maybe distributions that look like this, where most of our data is centered or is off to the left-hand side. And then maybe we have distributions like this, where most of our data is on the right-hand side. And this one is called right skewed. And this one is called left skew, which is a little bit weird. Right skew is the one that is facing the left, where most of the data is on the left. Left skew is the one where most of the data is on the right. The reason they are called left skew and right skew is while most of the data should be centered in the left, there are a couple of points that are dragging the center to the right, that are skewing our distribution towards the right. Likewise for left skew, most of our data is on the right, but there are a couple of points that are dragging the center to the left. And so it works a little bit opposite. I think it's a little bit counterintuitive. What you would assume is right skew versus what is actually right skew. Right skew means most of the values fall to the left of the middle. Left skew means most of the values fall to the right of the middle, which is confusing and a little bit backwards, but it's just the terminology that we have to learn. Certainly does not match this. If we had to describe this, there might be maybe a very, very slight right skew. Very, very slight, like maybe there's a little bit more on the left than there is on the right, but they're fairly symmetrical. Like it's mostly going to be symmetrical in this case. Questions with our histogram and with the shapes that our distribution can kind of take on preliminarily. My answer key actually says that it's positively skewed. I would probably accept either positively skewed or symmetrical for this. If I were to give you something like this on a test, I would probably accept both. Because I think it's fairly close. I don't know. It's pretty close. Yes, it's the frequency put into context. So 7 on its own doesn't tell us anything about like how much the bucket is filled. Relative frequency says, actually, I'm going to turn that 7 into a percentage so that we know, is that a lot or is it only a little? Yeah. Okay. Frequency polygons communicate the exact same information as our histogram. The only difference, well, there are maybe a couple of differences, but the only major difference is rather than using like the full spread of the x-axis as our x value, we are going to use a representative value from the bucket to act as the point that we care about for our frequency polygon. Where are we going to get these representative values? But which like value? So frequency was the y value, which we're still going to use. So we used the class boundaries before to find our x values.
We're going to use the other frequency.
So we'll use that one in a second. That'll be for OGIVEs. These are going to use the midpoints. All right. Remember, in this case, the midpoint is just a representative. It's just telling us, hey, this 5 tells me that I'm between 0 and 10. Hey, the 16 tells me I'm between 11 and 21. We're not really doing much with them beyond that. Right. So for instance, this point here would be our 5. This point here would be our 16. Here would be our 27. Our 38. Our 49. Our 60. And our 71. And very, very simply, we are just going to connect the dots. We're just playing a game of connect the dots. So from 5 to 16. And we're not trying to put like a curve to this. We're just going from one point to the next, connecting the dots. So kind of like, I mean, you'll notice I've overlaid it on top of the histogram. It really does communicate very, very similar information to the histogram. It's just using a slightly different metric for what points are being assigned. Right, so rather than kind of graphing the full kind of interval between A and B, we're giving it a little bit of movement, right? Connecting these ever so slightly more. Now this frequency polygon is almost finished. It's not quite done. There's a weird thing that we have to do with frequency polygons where we need to make sure that they start before we start seeing data and that they end after we start seeing data. So if we think of this 0 through 10 as like our first bucket, well, the frequency polygon is going to start in like this imaginary 0th bucket, and it's going to end in the imaginary 8th bucket that doesn't exist because we don't have data for it. We could construct what that bucket actually is, but there's actually an even easier way to figure out the representative value for that particular bucket. What do I notice about my midpoints as I go from bucket to bucket to bucket to bucket? Increases by how much? From 5 to 16 to 27? Increasing by 11. Where is that 11 coming from? Not the standard deviation. We'll get to standard deviation later. Yeah, it's the difference between the class boundaries. That is our class width. It's like the size, the length of a particular bucket. And so if we need to figure out what would be the representative value of the previous bucket, what would come before 5? Yeah, -6. Something like that. And what would come after 71? 82. Like that. So just making sure that it's It's almost like it's tethered to the ground. It's tethered to the x-axis. We start one bucket before we start seeing data. We end one bucket after we start seeing data. So we're starting at 0, ending at 0 for our y values. Okay. But otherwise communicating pretty much the exact same information that we were seeing from our histogram. Not really anything all that shocking. Any questions for our histogram or frequency polygons? That's what we're doing here. Yeah. Mm-hmm. You're fine. Again, I'm not collecting that. That is purely for your own learning. Yeah. So whatever you want to do to make it clear. But yes, it is kind of important to note the blue is one graph and the black is another graph. So if I asked you for the histogram, you don't need to put a frequency polygon on top of it. If I ask you for a frequency polygon, you don't need to put a histogram on top of it or under it. They are kind of separate from one another. But I have overlaid them here so that we can see very, very clearly they're really referring to the same thing. They are, for the most part, the same style of object. It's just a bit of preference which one we use over which. They're not going to really communicate different information. The one that is going to communicate different information, and for which I will need an entirely new graph, is the ogive. Okay. My x-axis, actually, I am going to do a new page here so that I'm not trying to cram in too much. X-axis is still going to be my boundary. This is my class boundary. My y-axis, which before was just the frequency, now is going to be a little bit different. This is now going to be the cumulative frequency. So we saw before that our cumulative frequency started at 0, ended at 255. So just to make that actually fit here, I did up by like 30. 90, 120, 150, 180, 210, 240, 270. I could probably do more refined now that I've actually given myself a little bit of space, but we'll just do this 30, 60, 90, 120, 210, 240, 270. We said this is the class boundary still, so still this negative 0.5. 10.5. All right. We said this is 30, 60, 90, 20, 210, 240, and 270. And very, very simply, we're just going to start at the leftmost boundary and work our way through the buckets, adding up as we go. So when I am at my leftmost data point, so before I work my way through the first bucket, how many data points will I have observed? None. So starting at 0. Okay. So from negative 0.5 to 10.5, I have now gone all the way through my first bucket. By the end of my first bucket, how many data points will I have observed? 7, which I'll put like here-ish, maybe. Okay, so from 10.5 to 21.5, I will have gone all the way through both my first bucket and my second bucket. How much did we say that was going to leave me with? 40. Right, so we've added another 33 on top. We're using that cumulative data. By the time I get through my third bucket, how much have I gone through? 108, which is up here. By the time I've gone through my fourth, 183, fifth, 221-ish, sixth, 244, and then last, 255. And just like before, just connecting these, we're not trying to add like a curve or anything to them. They're also not going to be perfect. That's okay. Just do our best to get it relatively close. Something like this. There are a couple of interesting notes in the 2.5 kind of completed notes about like characteristics of ogives. For instance, you would never expect to see the Y value go down. You're not going to look at a bucket and then lose data from what you've gotten previously. So the least a bucket can contribute is 0. So you might plateau a little bit, but you're never going to actually decrease, which hopefully should make sense, right? We're not going to ever lose frequency from our previous kind of sum, but getting exactly what you see here. All right, questions for this particular example? Just a quick, casual 55-minute example, 50-minute example. How are you feeling? All right. So we're going to have a quiz over 2425 on Friday. So not tomorrow, but Friday. The 2425 classworks are posted to Pearson, so you have access to both of those. Again, I have uploaded a brief synopsis of this, although this that I'm about to upload is probably a little bit more robust in terms of what to actually look for. I think this was a better done than what I recorded last night. And so you guys have the options of either working through the rest of this kind of 2425 work as practice for the quiz, or working on the classworks, which just like with all of our other quizzes, if you finished the 2425 classworks by the day of the quiz, then you'll get bonus points on the quiz. So up to +2 on the quiz. Cool. All right, you guys have the rest of this time to work on that. If you have any questions as you're working, of course, feel free to ask. I'd be more than happy to take a look.